So when you hear gRPC, what comes to mind? Probably high performance, HTTP/2 protocol buffers, right? And you're not wrong, but the real power of gRPC, it's not just about the tech. It's really a philosophy for building systems that just don't break. And it all boils down to one central idea, the contract. Let's dig in. Here's how we're going to break it down. First, we'll start with a super simple analogy I call the universal order form to get the main idea. Then we'll see how that looks as an actual gRPC contract in code. After that, we'll follow a single request all the way from the client to the server and back. And to wrap it all up, we'll put on our senior engineer hat and ask, what are the real-world trade-offs of actually using this? Okay, so at the very heart of any gRPC service is its definition file. You'll know it because it ends in .proto. But I want you to think of this as less of a file and more of a binding agreement. It's the single source of truth that every single part of your system has to respect. Let's make this really simple. Imagine a restaurant that has a magic order form. It's so perfectly clear and structured that any waiter speaking any language knows exactly what to ask for, and any chef knows exactly what to cook. You literally can't mess it up. There's just no room for ambiguity or mistakes. That is exactly what the proto file does for your software. It is the universal order form for all your services. But why do we even need such a strict order form in the first place? I mean, it seems like a lot of work. Well, to really get why this solution is so powerful, you have to appreciate the problem it solves, especially in today's world of microservices. Before we had these strong contracts, things were, well, chaotic. You'd have all these microservices, and one team's API might send a customer's name as first name, camel case. But the service that receives it is expecting first underscore name with an underscore. Now, that seems like a tiny thing, right? But multiply those little mismatches across dozens, maybe hundreds of services, and what you get is a really brittle system that's constantly breaking in subtle, super annoying ways.
Okay, so we get the why. It prevents chaos. Now let's get into the how. Let's see what this brilliant idea of a contract actually looks like when you write it down in code.
So a proto file has three main building blocks, and they map perfectly to our restaurant analogy. First, you've got the service. Think of this as the menu itself, defining a whole collection of related things you can order. Then you have the RPC. Each RPC is like a specific dish on that menu, a single function like getProduct. And finally, you have the message. The message defines the ingredients for your order, like a product ID, and the structure of the dish you're going to get back. And here it is all put together. A contract for a simple product service would define exactly those three things. You can see it has a product info service, which contains a product gRPC. And that RPC clearly states it requires a product ID message as input, and it promises to return a product message as the output. There is zero guesswork here. It's clean, it's explicit, and it's totally unambiguous. Now, here's where the magic really happens. You only write that one proto file. That's it. From that single source of truth, the gRPC tools generate all the tedious networking code for you. You can see it in the diagram here. It creates a server skeleton where you just plug in your actual business logic, and it creates a client stub that makes calling this remote service feel just like you're calling a local function. This is a massive productivity boost, and it just wipes out an entire class of potential human errors. Okay, so we've got our contract, and we've got our auto-generated code. Now let's look at the absolute simplest, most common type of communication in gRPC. It's called a Unary RPC. And Unary is just a fancy word that means one request gets one response. Simple as that. The best way to think about a Unary RPC is to picture a vending machine. You put in one coin, you press one button, that's your single request. A second later, you get one candy bar back. That's your single response. The whole transaction is simple, it's atomic, and it's complete. Done. Now, behind the scenes of that vending machine transaction, a few things are always happening. First, your client code calls the function on that stub we generated. Then, the gRPC library takes your request, converts it into a super efficient binary format, that's called serialization, and zips it across the network. The server gets it, converts it back, runs your business logic, and then it does the whole process in reverse to send the response back to you. And when you look at the actual client code, it's shockingly simple. But notice two really important things here. First, the call itself, client.product. It just looks like a regular function call in your own code. All that network complexity is completely hidden away. And second, and this is absolutely crucial for production systems, is the context with timeout. This sets a deadline. It tells the client, hey, don't wait forever if the server is slow or just not responding. This is a fundamental building block for making your systems resilient.
Okay, the code works. Great. But now let's shift gears. Let's go from just making it work to making it work reliably and at scale, and in a way that you can actually maintain it in a real-world production environment. This is where we need to put on our senior engineer hat.
You know, this is the one question that really separates junior from senior engineers. It's not just about writing code that functions. It's about writing code that can survive the absolute chaos of production. Now, gRPC gives us a ton of tools to help with that, but it also forces us to make some important trade-offs.
When you decide to use gRPC, you're making a deliberate set of trade-offs. You gain incredible performance because of its binary protocol, but you lose the simple, human-readable nature of something like JSON. You gain the safety of strong contracts, but you have to add a code generation step to your build pipeline. And while it's fantastic for service-to-service communication, it just doesn't work natively in web browsers. A senior engineer understands these trade-offs and weighs them carefully before picking a tool.
So beyond just getting it set up, using gRPC effectively in production means you have to navigate a few common pitfalls. Like, how do you update an API without breaking all the clients who are already using it? That means you need a real strategy for schema evolution. We saw timeouts on the client, but are those deadlines being enforced across the entire chain of calls? And is your code smart enough to tell the difference between a network failure and a legitimate error from your application? Getting these things right is what keeps a distributed system from falling over.
Ultimately, what happens is that using gRPC kind of pushes you towards better system design habits. It forces you into a schema-first approach, where you design the contract deliberately up front. It makes you think about API versioning from day one, and it brings these critical architectural questions right to the forefront. Can this API call be safely retried? That's idempotency. Should the client wait for an answer, or should this be an asynchronous call? So you see, gRPC isn't just a library. It's a tool that encourages you to think like a system architect.
So we'll leave you with this one question to think about. The very rigidity of gRPC, its strict contracts, the build steps, it can feel like a constraint, especially on smaller projects. But in a large-scale system with tons of teams and services, that same rigidity is often the one feature that prevents total chaos. So for your next project, you have to ask yourself, is that strictness a feature or is it a bug? The answer, of course, depends entirely on the problem you're trying to solve.